Welcome to the part 4 of lecture 1. This is the last part of this lecture. We are going to continue with the study of complex numbers. So in the previous lectures, we learned about all the good properties that the set of complex numbers have. They form a group with addition. If we consider also multiplication, they form a field. It's a closed field, algebraically closed field. It means any polynomial, any non-constant polynomial has roots there. If it's degree n, it's of degree n, it has n roots considering the multiplicity, so it's great, right? Although the set of complex number has all these good properties, there's a property that the field of R, the set of real numbers with addition and multiplication has, which C doesn't. So R is not closed as a field. It's a field, but it's not closed. But it has another property that C doesn't have. R as a field is ordered. What does it mean? If we pick any two real numbers, x and y, any two real numbers, one of the following things would hold. So either x is less than y, or they're equal, or x is larger than y, right? There are two extra algebraic properties that these inequalities would satisfy. One, if A is larger than B and C is larger than D, then A plus C is larger than B plus D. This is axiom number 1 or property number 1. The property number 2, if A is positive, it means it's larger than 0. If B is also positive, their product, the multiplication of A and B, would also be positive, right? Any field which has an order that satisfies these two properties is called an ordered field. So the essential thing about C with addition and multiplication it has is that it's not an ordered field. So, for instance, we cannot say if I, the square root of -1, is positive or I is negative. This does not make sense. Why is that? Why there is no order on C? This is a fact. There is no way to compare elements of C to say one is larger than the other. We can prove this. We can do it by contradiction. So we can do this by contradiction. It's actually good homework to think about, good exercise. Let's do it. So proof by contradiction means suppose we have C with addition and multiplication. Let's say we do have order on C. So if I consider the imaginary number I, it's either positive or negative, right? So 1, possibility number 1, I is less than 0. Possibility number 2, I is larger than 0. There is no possibility number 3 because I is not equal to 0. There are two different numbers, right? So it's either I is less than 0 or it's larger than 0. If we get to contradiction in both of these cases, it means there is no way to compare I to 0. So let's consider the first case. Let's say I is less than 0. Okay, what would happen if I is less than 0? So the first thing one should argue is that we can add minus I to the both sides of the inequality. So if I is less than 0, I plus minus I is less than 0 plus minus I. But the left-hand side would be 0, and the right-hand side is minus I. So minus I would be larger than 0. But if minus I is larger than 0, we can repeat the same statement, and then using the fact that if A is positive and B is positive, A times B is positive, we get minus I times minus I should be positive. And we know minus I squared is -1, so -1 should be positive. You might say this is a contradiction, but it's not yet a contradiction. Because although in the set of real numbers, it is correct that -1 is a negative number, but maybe there is a weird order on the set of complex numbers, that in that order minus one is positive. It still is not a contradiction, but we are very actually close, right? How can we progress? How can we proceed? So to finish the proof, note that we had minus I is positive, right? Right here. So if minus I is positive and minus 1 is positive, their product should be positive, but minus 1 times minus I is I. So this means I is positive, right? But we started with the assumption, considering the case where I is negative, and we arrived to the conclusion that I is positive. Now, this is a contradiction for the first case. Now we should consider the second case. If we get to contradiction in the second case too, then we're done. Now let's consider the second case. Consider the case where I is a positive number. Right. If that's the case, by just writing the same inequality twice, we see that I times I should be also a positive number, right? I times I should be larger than 0. That means minus 1 is larger than 0. But I is larger than 0, minus 1 is larger than 0, so their product minus I is also larger than 0, right? Now, I is larger than 0, minus 1 is larger than 0. Their sum implies 0 is larger than 0, and that is a contradiction. That is not correct. Okay, so we learned C has great algebraic structure. It's closed as a field, but it's not ordered. In the next lecture, we start considering the set of functions on C, consider holomorphic functions on C, and later we would move to study holomorphic functions in higher dimensions, higher complex dimensions. That would be the stepping stone to go towards algebraic geometry.